for everybody for coming. So let me start with a zeros example of the mirror symmetry for a open Riemann surface, which is the example of a cylinder. A lot of the mirror symmetry people already know. So I'll draw a cylinder, and so this would be S1 cross R. Because this is a non-compact surface, instead of the mirror symmetry statement, the usual Fukaya category will actually consider the RAF Fukaya category. The name sounds more complicated, but actually it's easier. And so for RAF Fukaya category, not only we have so the objects of the categories are all the Lagrangians, or the Lagrangians in here, because it's just 2 dimensions, so the Lagrangians are all the curves here. And then, so for RAF Fukaya category, not only the compact curves, but we also consider non-compact curves. But there are too many things, so we just actually, one can show that the RAF Fukaya category for the cylinder can be generated by just this Lagrangian that runs through the cylinder horizontally. And so this is a cylinder. And so that means all the other Lagrangians can be obtained from this one by some categorical operations. So then we'll just only look at this Lagrangian and do algebras with this one. Okay, so that's this Lagrangian L is the object. And so for 2 objects in a category, we want to know what is the morphism complex. But we only consider this one object, so the other object is just itself. And so let me draw another copy of L. This one, so this cylinder has those cylindrical ends, but then we can also think that there's this compact part in the middle. But so anyways, so let me draw another copy of L, but I don't want to draw it on top of this one. So I'll draw another one that's a little bit, so there is a transverse intersection with the previous one. Oh yeah, and I do want this L. So in general, I want this L to be exact Lagrangian that's conical in the cylindrical ends. Okay, but in this picture, it's just this one. And how do we define the morphism complex in the RAF Fukaya category? It's going to be the RAF fluor complex between L and L. And let me spend a couple minutes defining that. So in order to define the RAF Fukaya category, we need to pick a Hamiltonian perturbation. So the Hamiltonian perturbation, I'm going to pick actually a sequence of Hamiltonian perturbations. Let's just say H1 is 2 pi r. So r is in this direction. Okay, and then the S1 is in the theta. I won't use the theta. It's in that direction. And then, so there are H2s, which is just 2 times H1, and so on. Hn is n times H1 as n goes to infinity. So, and once we have this Hamiltonian, we can define a ordinary, let me write on this board. We can define an ordinary fluor cohomology complex perturbed by this Hn. What is this? This is this is vector space. It's got some generators. So the generators are it's this one. I'm going to label this guy 1. It's just a random label for now. And so what are the generators of that one? Because of this definition, the generators is going to be the time 1 Hamiltonian trajectories that starts in this L and ends in that L. So what are those? Those are really the rip chords, if you consider this as the symplectization of this contact boundary. So that it looks like chords that starts in L and wrap around here and then ends in this L. And the length of the chords is given by the slope of this linear Hamiltonian. I should say this Hamiltonian is this one for r bigger or equal to 1. So this is defined. It looks linear near the ends of near the infinity of the cylindrical ends. But looking at chords is a little bit complicated visually. So it's actually equivalent to if we perturb this L, so there are two L's. If we perturb the first one by the Hamiltonian flow, by the Hamiltonian action, and then the trajectories, it's equivalent to count trajectories starting from L to L. That's equivalent to say, I'm going to perturb the first one and then just count the intersection points. So if I perturb this one, those trajectories are, once I perturb this one by the Hamiltonian flow, the trajectories are going to be equivalent to the intersection points. So let me perturb it once. And then I'll do it the same on this other end. Okay. And then I end up with two more intersection points, points here. Let me label this by x1 and x minus 1. Right now, it's just completely random labels, just trying to label the points. So that's if we perturb by h1. So this two used to be the rip chords. Now they're intersection points. Oh yeah. So then the h2. No, actually, it becomes constant because we are. See.
Just move over time 1.
Yeah,
so you would just make a certain turn. For the next one, you turn twice.
Yeah, the derivative of this is constant. So it says when r is very big, it's constant.
Implicitly, the h1 is constant or 0 in the compact part, and then it goes up.
Yeah, yeah. Actually, it's linear near the ends of the cylindrical end.
And since linear is just a fixed move by a fixed angle, out very fast.
Yeah, so it moves from here to here. So it's constant here, and then in the middle it turns once. And then for h2 it turned twice. So in general, this space is generated by the perturb the first L once, and then look at the intersection points with the next one. So for h1, there are 3 intersection points that are the generators. And then as n increase, we just get more and more generators. And this space is defined to be some kind of a limit. Normally, it's a harder limit of some homotopy direct limit. But in this one, it's fairly simple. It's just a direct limit. In this case, it's actually just you take, we can see that all the intersection points when after h1 perturbation is just this 3, and then after the next one, we get another one here, and then this one is included in the next complex. So as n goes to infinity, we get infinitely many intersection points on both ends. And the previous one is included in the next one. So this is just take everything, and there's an equivalence by inclusion. And so this complex, this wrap Floer complex is the limit of the ordinary Floer complex perturbed by this Hn. And this space is generated by all this xi's, where I is in Z. Okay. And so So this is just what this space looks like, and there's an algebraic structure on this by counting holomorphic triangles. So what triangle we count is there's a product structure where we count things that we perturb the first. There will be 3 L's. Now we perturb the first one twice, and then so that's twice the speed of rotation, and then perturb the second one once, and then now perturbing the third one. So if we try to do that, we have one. We have another one that I'll just draw part of this that rotate twice as much as the yellow one, and then here, and just roughly to see that there's, for example, there's this holomorphic triangle. And then for the red one, this one, because this is the first intersection, it's actually x1 for the first one. Well, I just do this label and count the holomorphic triangles, and then we can actually see this triangle tells us there's a product structure that says x1 times 1 equals x1. And then you can do that for everything, and turns out the labeling here is not random. They actually are based on algebraic structure, like multiplying the monomials together. So here, this one has a mirror, which is C star, and this object corresponds to this sheaf O on C star, and we just computed that the endomorphism algebra for this is the Laurent polynomials, which is also the endomorphism algebra for O. And turns out in this case, there are no higher order polygons. So this is the infinity structure. And I feel like I'm running out of time. How much time?
No, you are blessed. So
Oh, okay.
4 minutes more.
Okay, that's good. Okay, so that's that case. Now we can play this game for a general Riemann surface. Let me draw it here. So all this punctured Riemann surface are Liouville manifolds, so we can define the Foucault category by Apuzet-Saddle's work. And we can play this game on this surface, any punctured Riemann surface, and we'll learn a lesson. And the lesson is we don't want to count holomorphic disks because they become intractable to count. And so we want to find a way to better way to compute it. And I say this kind of surface, I want to think of this surface. There is a way by Grisham-Minkowkin that can decompose any hypersurface. So this is I want to think of this hypersurface, so Riemann surface as hypersurface in C star 2. But in general, in hypersurface, any projective toric variety, there's a way to decompose them into a pair of pans. So so I want to think of only the hypersurface in C star 2 that belongs to a degenerating family near the tropical limit. So there are some Laurent polynomials we can write down. Let's not get into the details, but this is a Laurent polynomial with finitely many terms. And if the way to decompose into a pair of pans is if we take the log of this goes into the singular locus of the max of some kind of function. That is a maximum of a set of convex linear functions, and in this picture, really it just degenerates into this picture. And to just a quick example, for the pair of pans, which we previously know what the mirror is, which we know the homological mirror symmetry story of. Okay, so just pair of pans, that degenerates into something like this. This is the singular locus of the functions 0, C1, and C2. And so what is a mirror? So Abuzid, Rukazakov studied the SYZ mirror for this and had a prediction that the mirror for this is some complex three-dimensional toric manifold with a superpotential. There's a holomorphic function from X to C. The mirror is a Landau-Ginzburg model. So what is this complex three-dimensional toric variety? It's actually, we can look at this picture and get a this is a 2D picture. We can get a 3 real-dimensional polytope out of this by introducing a third coordinate, and that third coordinate, eta, is bigger or equal to each one of these functions. So this third coordinate is bigger or equal to 0 right here, and bigger or equal to this function C1 here, and then bigger or equal to this function C2 here. So it looks like the corner of a wall tilted. So, and then this is the, well, so when we fold this up, this is the moment polytope for C3 in this example of a pair of pans. And the superpotential is a toric monomial that vanished to order 1 on each of the irreducible toric divisors. And in this case, it's the multiple of the coordinate of C3. So the toric divisors are just x equal to 0, y equal to 0, and so on. And we can do this to this picture too. There are some functions we can put on this, and then it just looks like this picture folded up. That's the moment polytope of the mirror. And the point is, the mirror you can cover this by things that looks like the corner of the wall, which are mirrors to the pair of pans. So there is this cover of the mirror by affine toric, by like this affine charts. And then the B model for the mirror symmetry story is that what we really care about is this thing called the category of singularities, which is some kind of sheaf. So by definition, once we have this cover, we can compute this from the pieces. And what I showed is that the A set, of course, there are some like conjectures by Seidel, and like I just completed that story, that the A set, the symplectic set, can also be computed from knowing the pair of, the Raffaelli category of the pair of pans. And sorry for going over time. So I just want to end. So we know how to compute the to do the mirror symmetry for this puncture surfaces, but I just want to end with the question that I really want to do this for hypersurfaces in C star n. And I think philosophically, maybe we can try to decompose into pair of pans as well and try to do something like this. Okay.
Thank you very much.
Good.